Welcome to week 5, Biological Earth and Space Sciences. Our topic this week is scientific thinking, so we're going to do a brief overview of this, given that most of you are doing a lot of scientific thinking now for assessment task number 1, which is due very soon. Obviously you'll be demonstrating your interpretation of the Australian Curriculum for Science, and you'll also be demonstrating the application of that and the elaborations of that through certain processes using one of our 15 topics. But for today, let's have a look at the topic. It's scientific thinking, and basically what we're going to do this week is go through the following items. We're going to look at the 5 E's and the POE model. Now, in some countries it's P-O-E and E, okay, and I'll explain that shortly. But we begin Linda's resources this week with the Year 5 students' representation of science, and as you can see, it's very much inquiry and experimentation driven. So you can see the machinery, you can see the lining up of the lab, the desk, you can see the connection, the thought bubble in the student's mind leading to the real world situation. I'm not quite sure what the red thing is there. Seems to be some sort of a neuron twisting or something happening there. And here, of course, we've got some natural applications as well. This probably looks a little bit like a DNA, and we can see some strands, etc., interwoven. So the student's bringing together a lot of different aspects of science here, including the experimental, the applied, and of course the natural sciences. The topic we're looking at this week is the 5 E's. And we're also going to look at the POE model as well. And basically the presumption here is both of these can be used to encourage your student and yourself to work scientifically in a classroom. And they can also add a real fun dimension to things as well. So the learning outcomes for this week, again, explain, describe and outline. So explain the role of investigation in science education, describe 2 approaches to thinking scientifically, and outline the process of fair testing. Okay, and when we look at the notion of fair testing, it's an important one that we apply, and this little cartoon demonstrates that. Humble primates could ever discover such metaphysical entities now looks arrogant, dangerous and rather odd. The second formation, of course, but this informed skepticism can be a positive thing. And the final thing, it should make us suspicious of charismatic gurus, inflammatory political leaders, and all those who claim they have a hotline to the moral truth. So it's a really interesting notion here on science. It's about actually building evidence, compiling a case, and conducting a fair test. The launching pad this week, we've got basically 5 aspects, 5 dot points we need you to understand. First, the notion of an investigation. It's a scientific process of answering a question set, exploring an idea or solving a problem. POE is to predict, observe and explain. The 5 E's is a 5-stage teaching model, of course coming out of primary connections, that focuses on student learning by becoming engaged in an activity that links their prior knowledge with exploring and then elaborating on the new knowledge about a new concept. The idea of a fair test, if there is such a thing, using controls to change one variable, an independent variable, to measure the effects, dependent variable, in a cause and effect of investigation. And the independent variable in this case, of course, is what you change. The dependent variable is what you measure. So it's the whole notion of a fair test. The investigations? Well, we use investigations for a range of purposes. And the first, obviously, is to actively engage students in learning. So it's the hook. It's the kinesthetic hook. So we really want to get students into the science process, into reasoning, and into exploring the question why. We want to also, the second point, we want to provide students with opportunities to learn the skills and processes of investigation. So again, it is a rigorous process. We want to imbue it with some rigour, and we want to build some respect from the students around that notion of scientific rigour. The third thing we want to do is provide an authentic experience of science. That is, we've got to situate science in an authentic setting, and we can actually explore how science can then be connected to real-world outcomes, and through the manipulation of independent variables, we can actually show how science can lead to different outcomes. And finally, we want to assist students to develop an understanding of scientific evidence and the nature of science. And these are all important things that we've explored in previous weeks. What constitutes scientific evidence? And of course, why study the nature of science, which came from week number 3. Little cartoon there. Our biggest threat to our survival is us now ourselves. and we can destroy ourselves and our planet quite easily with a combination of ignorance, selfishness and lethal technology. So again, the whole notion of investigation, very much at no point in history has mankind been in more control of his destiny than he is now. And of course the scale and scope of science is a big part of that. POE, or sometimes POE and E, have a look at this whole notion of exploring. It's an 8-stage model, and the material I'm presenting to you comes from Josh Haysom and Michael Brown from the National Science Teachers Association in Canada, and the Canadians have been going down this track for a good two decades now, and they're generally considered perhaps the best in the world. And the Canadian education system's right up there with the Finnish in terms of leading the world education system. And they've put together a little book called Predict, Observe, Explain, where they have 15 chapters which explored different aspects, and there's 15 experiments in each chapter, and it's over 300 pages long. And they actually use the POE model to actually demonstrate application to everything from forces right through to heat, right through to friction, and they demonstrate all of these different simple exercises where you can use prediction to actually set up the example, and you do that in quite a rigorous way. And once you've set up the example using prediction, of course you can use observation to actually have a look at how your predictions are going to perform, and then of course experimentation is the final stage, where you can actually test your understanding, and sometimes in other countries they add the E to it, ultimately evaluation. Now in this model they call it follow-up, but when we look at it, the first step is really orientation and motivation, where we take the learner and we place them. We begin by drawing on the student's past experience or their previous understandings, and we raise a challenging question that can be addressed through an experiment that might follow. A few minutes of full class discussion is usually a good opportunity for the students to provide them with the opportunity to reflect on their past experiences and their understandings. So it really is the laying of the groundwork, the mortar. Step number 2, introduce the experiment. Introduce the experiment. Link it to the previous discussion will help it make it meaningful. And once you've linked it to the previous discussion, you're building that sense of relevance. You are kind of escalating the rationale, the application, the situatedness of your particular science. Step number 3 is the elucidation of student ideas, and here's where the prediction begins to come in. Students list their ideas basically before they do the experiment, and sometimes we use a worksheet, which is generally the most acceptable way of doing it. Particularly working with a large group of 30 students, you have to focus them, so it's always good to focus them on a worksheet and what they predict will happen, along with the reasons for their predictions. And I've got an example to show you shortly. The exercise is valuable for both students and the teacher because it puts you all on the one page. And when you think about it, a good POE lesson we can get to step 7 in about 40 minutes. So the whole aim is to get this inquiry process up and running really quickly. So it provides the teacher with useful insights and an opportunity to plan ahead. You can actually predict what students may be thinking. You can give them one of 4, for instance, outcomes, and they get to elect and choose which outcome they think is going to happen and justify it. And you can also circle around and talk to individual students as they're completing their predictions, and it's a little bit almost a little bit like progressive research, formative research, almost a little bit like stimulated recall, because as the students doing their prediction, you can talk to them about what they're doing and why they're doing it and what they're thinking. Step number 4, discuss their predictions. So you don't just go from making predictions straight into action, you actually discuss them, and it's a 2-stage process. First, you've got to ask their students to share their predictions in a full classroom discussion. And a chalkboard or a smartboard is fine to highlight their predictions, a whiteboard, a little concept map, the predictions and the reasons for them. Now this needs to be handled sensitively, and on account some students feel quite anxious based on the fact that there may be a right or wrong answer. Hence you need to be supportive, you need to be encouraging, and you need to be diverse. You get many students and their viewpoints out. And just remember, the rule here is there's no poor ideas. All ideas are valued because they represent the best efforts, and the best efforts of students to make sense of the world, which is what science is all about. Remember, we're not about the old right answer, correct answered scenarios anymore. We're actually about the inquiry process. So you might explain that making our predictions explicit helps us to learn. And after this has been done, you might invite the class to discuss what predictions and reasons they now think are best. You can even ask them to vote. When students can reconsider their reasons, some may begin to change their minds and reconstruct their thinking, so build in time for that. Immediately prior to the experiment, it's often fun and illuminating to have a straw vote about the outcome. So, create a little bit of an exercise there, a little bit of gameplay around that. Step number 5 is observation. Now, most experiments in a science classroom are designed to be done as demonstrations, which is a little bit sad, although some make good student explorations. It is possible in many cases for students to actually build and conduct their own experiments, and I would encourage you where possible to do that. And if you can't do that, for instance, get an artifact that can do that for you. This is one of the reasons I use robots, because they can be adapted to suit many different scenarios, everything from levers and pulleys right through to push and pull, right through to friction, right through to surface tension. All of these things can be used and demonstrated using the one artifact, a robot. So it's quite a dynamic and flexible tool. Invite the students to observe the demonstration or to complete the demonstration, usually in pairs or teams. And once they've done it, ask them to write down their observations. It's really important that they write down their observations, because that's what we're going to discuss at the later stage. Step number 6 is explanation. Students often reshape their ideas through talking and writing. And I've often found that it's useful for students to discuss their explanations of what they've observed with a neighbour, in a small group, in a jigsaw group, before they actually formulate a written explanation. And they also seem to find this reassuring too, because it takes the element, the risk-taking out of it, and builds collaboration. And after they've done this, collect an example or a sample, a range of them, and have a full class discussion around them as you see it appropriate. Step number 7, the scientific explanation, and you've got to provide that as the teacher. You can do that by building on what the students have presently presented. Or you can begin by referring to the field of science itself. Certain scientists currently think, rather than saying, this is the right answer. Okay, try and avoid that. Many teachers choose to ask the students to write the explanation in their notebooks or on the back of their activity record. This is obviously the learning, the rehearsal stage. Okay, they've been through an experiment, they've applied the learning, they've tested the learning, and now they're rehearsing the science behind that by noting it down. The students might then be invited to compare their explanations with those of scientists, and again focusing on the similarities and differences. Another chance for them to reconstruct their idea. For instance, a student may predict the right outcome, but may do it for entirely obscure reasons. And here's a really good chance to link the learning for them, to help build that learning chain. Step number 8 is the follow-up. And researchers using the POE model have found that students' ideas are often resistant to change. And there's no guarantee that a POE will do the trick, even though it might provide a valuable learning moment. And the same thing with field trips too. Students may have preconceived ideas, and you're not going to shift their thinking, but you're certainly going to shake it. And that's the whole point of scientific inquiry, to shake their understanding. So you're going to facilitate this. Steps 1 to 7 usually get done in about a 40-minute period. If you have a class that's moving a little bit more slowly, or if you enjoy teaching a little more slowly, remember this is pedagogical choices you're making, sometimes it's good to take a step after a break after step 5, the observation, and set the next step for the students for homework, step number 6. Always good homework task. So you can actually break this up, you can self-pace it. Okay, so steps 1 to 7 are usually considered to be done in about 40 to 50 minutes. It's a pretty fast-paced lesson. Or if you go a bit slower, take a break after observation and think about step 6 as homework, step 7 and 8 as you, the teacher, coming in doing the final clean-up, the final wrap-up. And you can look at it, steps 1 to 4 are basically about probing your students. Orientation, introducing, prediction, discussion of predictions, about probing the students' conceptions. Steps 6 and 7 enable you to monitor your students' efforts to reconstruct their thinking. You're giving them, what we call the double loop learning opportunity. And step 8 provides you with feedback on student progress. Okay, so you're actually able to get back to them and give them feedback on their progress. So you can get a fairly authentic response, moving from the initial encounter with a piece of science right through to a reformatted and reconstructed experience of science. And that way it becomes possible for you to adjust your teaching and to plan for subsequent instruction, making you much more effective as a teacher in the science classroom. It keeps you tuned, it keeps you focused, and it keeps you connected to your students. The stages, the major strength is they can continually provide you with insights into students' thinking, and I'm just reinforcing some of those points there. Steps 1 to 7 for steps 6 and 7 for monitoring, steps 1 to 4 for initial conception, and they are authentic responses that you're dealing with all the time. You're not dealing with a scientific principle, you're dealing with students' responses to science. Here's an example. Newton's first law, balanced forces. You can see it's pretty traditional. Okay, I've deliberately gone with something traditional because when you go around schools you're probably going to see a lot of this in your placement. It's a worksheet. Nothing strange about that. It's entitled The Bricklayer's Problem. You can see a bricklayer is building a chimney. He sets up on a pulley at the edge of the roof. He fills the bucket with bricks. It weighs the same as he does. He wonders if he's going to be able to lift it. Can he haul it to the top? He tries. What do you think's going to happen? Okay, let's how can we do that in the classroom? How can we replicate that experiment? Brainstorm. Have a brainstorm session. And then come up with your, okay, here's what we're going to do. We are going to actually design a small experiment using a small A-frame and a piece of string and 2 objects of the same weight. And then we're going to set the experiment up and see what happens. And I want you, as students, to actually predict what you think is going to happen. A, it will stay the same. B, there'll be an equalization. Or C, there'll be a shift from one side to the other. And as you can see, you then get to explain. You then observe what happens when you do the experiment. And then you try to explain in your own words what actually happens. So we can see it taking shape. And the scientific explanation, in the pulley problem there is no movement. We can go on and talk about the downward pull of gravity on each side of the pulley must therefore be the same. And of course they're the same weight. The mass of the bucket of sand and the mass of the wooden block are therefore the same. This is Newton's first law of physics. Okay, it's just a little sand is added to the bucket. The downward force on that side is greater. However, there'll be no movement if it cannot overcome the frictional force between the pulley and the axle. So it introduces a different concept here. So why doesn't just a little bit of sand shift it? Okay, friction. Second scientific concept. If more sand is to be added, the downward force increases and the bucket begins to move when the frictional form is overcome. And because the bucket accelerates, the speed at point B is greater than point A. And even if more sand is added, the acceleration is even greater. Okay, and of course Newton derived his own formula for that, F equals m by A, or ma. So we can see the scientific explanation there, and we can actually then test that using a few different principles by adding blue tack, for instance, by adding a few other stickable substances to see how the actual predictions are lived out through observation. Student explanations are really worth looking at. First year university physics students, 27% thought the block would be heavier, which is really interesting. And some attributed this to the block being closer to the floor, which is because it's at a lower altitude. Just more than half made the correct predictions about what would happen when sand was added, and this is first year university students. However, 30% predicted a new equilibrium position would result, that is number B, as if the position and not just the net force affected the system. And 90% of students correctly predicted the speed of the bucket would be greater at the lower mark. So you can see a great variation even in first year physics students around these simple scientific principles. We can take POE one step further. Science, geography, take an issue of importance to the wider society, pollution, global warming, water management, fishing, where there are conflicting points of view. create roles to reflect different groups in society who have a stake in that issue, including businesses who provide jobs, and create a scenario where resolution of these conflicts is needed. You can see a role play can work just as well, providing you keep them simple. The 5 E's. The Australian Academy of Science Primary Connections. Okay, and we have a simple solution here, or resolution, or proposal. All cats have fleas. Tiddles is a cat, therefore we should keep him off the sofa. Now that's a false argument. It says he's an intelligent but smiling partner. We can see over here that we've got Lyotard and Derrida. And these are two postmodernist thinkers who are very suspicious of the concept of reason. We maintain that reason is itself a fiction because it is a human linguistic construct, not a transcendent entity. In other words, reason doesn't exist of its own. It's actually mediated by people. Derrida, who's a brilliant theorist, said it is partly the worship of reason that has been the cause of so much self-inflicted human suffering. And of course he has a huge point there if we look at the current scenario we find ourselves in. With industrialisation and mass production and degradation of the environment and overpopulation, there's a lot of things there that we could actually attribute to the concept of reason and advancement. So the elaborations of the primary connections 5 E's model. Now we can see that it's engage, explore, and so on. Okay, the 5 E's. And the elaborations document is linked from the Moodle page. And as you can see, the purpose of engage is very much just like the POE model, to create interest, to stimulate curiosity, set learning within a context, to raise questions for inquiry, and to reveal students' ideas, beliefs, compare students' ideas. So in some ways the 8 stages of the POE have been collapsed into the 5 stages of the 5 E's. Okay, how would you do it? Now, one of your activities this week asks you to introduce a task using the 5 E's. How would you motivate students? A multimodal text, okay, discrepant experience, create interest and raise questions, okay, what happens in one country, what happens in another, open questions, individual student writing, drawing, acting out understanding, a role play, a discussion to reveal students' existing ideas and beliefs, okay, and from there you can move into the explore stage where you can start to explore these, a form of diagnostic assessment. Probably diagnostic is too strong a word, I would say formative. Here we have the quantitative version of it, where we're setting out the scene, we're marking the terrain. We then begin to explore that. We provide experience of the phenomenal concept under question. We can explore and inquire into students' questions and test their ideas, solve their problems. Okay, and this can be done through observation and measurement. We can test the ideas in classroom experiments, again, falling back on that. Where possible, however, do try to take students out if you can to do science, and do try and have the students acting as scientists as well as thinking as scientists. I know it's not possible all the time, given the limitations of equipment, but it's fabulous if students can actually do hands-on stuff. The investigation of text-based materials, newspaper articles, web articles, consideration given aspects of critical literacy, some of these other related competencies, making judgment about the reliability of the sources or the scientific claims to be made in text. We can go on, explain, and you can read this for yourself. Okay, construct multimodal explanations and justify claims in terms of evidence gathered. Consider current scientific explanations, and some examples here. Some of the elaborations that you could do in a classroom. Student reading or teacher explanation to assess concepts and terms that are useful in interpreting evidence and explaining. Small group writing is often a good one. Or design. And design can be a whole range of things, from poster sessions and techniques are fabulous, to generate a communication product, oral reports, formal written reports, PowerPoint, cartoon strip, drama presentation, a letter, a research project, with attention to form or of argumentation, genre, function, audience, and the integration of different modes. Once again, I always use robots in conjunction with these sorts of tasks to build related critical literacies. There is no point having sophisticated scientific understandings if you can't communicate them. Elaborate. Once we can explain, we can then elaborate, use and apply, reconstruct and extend. Look at some of these transitive words. Okay, quite powerful. Student planned investigations, exercises, a field trip, further reading, A communication product once again. You could have your own science conference, a science fair, a day on the field, a whole range of things that you can do. And the final thing is evaluate. And here again we can see with the, in the POE model we've got follow-up. But evaluate. Provide an opportunity for students to review and reflect on their own learning and new understanding and skills. Provide evidence for changes. And again, discussion. It's very much a replication of the POE, except evaluation is explicit in this one, where POE is more loosely called follow-up. So in activity 2, you had to choose a strand from the ACS and use the elaboration. So one of the strands, for instance, the one I've chosen, I actually think for this one I chose Earth Sciences, I think, had to do with the environment. Again, one of the topics I would probably look at here would be learning how Aboriginal and Torres Strait Island concepts of time and weather explain how things happen in the world around them. And I think that lends itself very well to some of the Dreamtime stories. Linda gave this particular example in the subject site, Year 3 Biology. Select the content. She took living things, non-living, once living. Discuss how you would engage students, okay, by having a host of objects, okay, an interactive table. Okay, living, not living, why? How do we classify things? What is an animal? What is a living thing? What constitutes a life? Then looking at a cake, simple thing like a cake, breaking it down. What are the ingredients? Where did they come from? Which one of them are living? Are any of them living? Which were once living? It's a really powerful inquiry. At a Year 3 level. Research coming out of the Australian meat industry 2 years ago actually demonstrates that less than 30% of students actually know where a lamb chop comes from. Now, you may actually think that's a good thing, but again, think about it. What does that do to our attitude to the environment? If we grow up not knowing, not being informed of what a lamb chop is, of what, for instance, steak is, all of these essential food groups. And we're growing up, and yet we're forming and shaping our own attitudes about food with very, very little evaluation of the sources behind those choices. And I take us back to one of those previous cartoons. We have within our hands the capacity to shape and structure our own environments. To what purpose do we want to do that? To what sort of thinking do we want to lead our students? Fair testing, okay, is talking about testing an idea. And fair testing means, you've got to follow a format. If something's fair tested, then it basically means that something has been explored in a rigorous way. And what's more, if it's been explored in a rigorous way, it's replicable. Somebody else can do it, and the results are therefore generalizable. They can be generalized to other situations that are the same, to other conditions that are the same, and to other variables that are the same. So it really creates the conditions for Karl Popper's falsification principles. If we really are going to test our science and test our scientific methodology, then we need to follow a rigorous format, and we need to keep following it until we can falsify something, and that disproves it. And as Popper says, all a scientific theory is a theory that's yet to be falsified. Nothing in itself is true. And it's a very powerful statement. Change. Okay, for instance, we may look at the amount of salt. An experiment. We take 2 plants, and we're going to vary the amount of salt we put in the water with one plant and reduce this out, or have normal water for the second plant. So look at the independent variable in this case is the change we introduce, okay, which is going to be the salt. Okay, the dependent variable, of course, is going to be the height of the plant. Okay, the type of plant is going to be the same. The amount of water we use is going to be the same. The amount of soil and the amount of sunlight. So these plants will be identical. They'll be sitting side by side. The only difference will be the amount of salt that we place in the water. We're going to see and test and measure what happens to the plant given different levels of salt in the water. So the following sentence may help you to plan your investigation. What happens to the height of the plant, the dependent variable, when we change the amount of salt added, the independent variable? Very clear and simple experiment. How can we describe the effect? Well, we measure it. What will the data we collect look like? It could be centimetres, it could be the conditions of the plant, it could be the colour of the leaves, it could be leaf spotting, it could be that, for instance, some of the related conditions, the plant in poorer conditions with poorer immune system may in fact attract bugs, may in fact attract mites, may in fact attract some of the negative parasites that come and damage plants. They're in poor health and poor condition and immuno-deprived. So how do you do this in your classroom? Well, here are a couple of possibilities. The Moodle sends you on a little journey this week to look at different classrooms, but I know at the back of your mind you're actually thinking about assessment task 1. So, we're looking here at what sort of possibilities can achieve these in your classrooms, and we could replicate something like the little pulley experiment. We do balanced and unbalanced forces, Newton's first and second laws of motion. We can test some quite established science from Newtonian principles. We could look at towing a trailer, Newton's first and second laws of motion, and again, Lego robots fit in beautifully here. A tug of war between a group of students, a tug of war with students pulling a rope against a tree, and have a look at the action and reaction forces, find ways to measure it. Okay, and that can be measured with a force meter. So there's a whole range of ways of looking at these. The question of which falls faster: gravitational force and motion, golf balls, ping pong balls, coins, feathers, if we want to go back to Galileo. Okay, and hopefully we have checked out that Galileo experiment. It came up in the Zoom session of 2 weeks ago. And it proves that Galileo was actually right. Once we take away gravity, a feather and a coin will fall at the same rate. And which leads us to our next one, the feather and coin mystery: gravitational attraction and air resistance. Reducing friction, frictional forces, might seem quite complex, but again, it can be done quite simply just by moving books. We're looking at the area of contact with the surface, moving books, put them on their end and move them with a force meter. Measure the force, put them on their side, move them with a force meter, measure the force, and it tells you a little bit about the power of friction. Having said that, I'm going to end the content session for this week. The Zoom session, Wednesday 10 to 11, will primarily be addressing the assessment task 1 and going back over some of the aspects of this week's activities. I'll also be looking at the forums and seeing if there's any comments there in the forums, with a view to being able to summarise those for you and answer any questions that may come from that. Good luck. Please keep the questions coming in. Keep an eye on the date, and please, if you do need to negotiate an extension, make sure you make contact with me in plenty of time so I can formalise that and set that up for you as a result of the cyclone and the issues that has created for everyone. Alright, stay dry and thank you.